Alpha Centauri is not a single star, but a triple system, the nearest stellar neighbors to our Sun at a distance of 4.37 light-years. For over a century, astronomers have studied this system with increasing sophistication, mapping the orbits of its components, measuring their masses and luminosities, and searching for planets that might harbor life. The system consists of Alpha Centauri A and B, two Sun-like stars locked in a mutual orbit, and Proxima Centauri, a small red dwarf that orbits the pair at a vast distance. This proximity has made Alpha Centauri a target of intense scrutiny and a focal point for speculation about interstellar travel and the search for habitable worlds. What was thought to be understood about this system, built on decades of observation and theoretical modeling, has been fundamentally challenged by data returned from the James Webb Space Telescope. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here, and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now, dim the lights. Maybe turn on a fan for that soft background hum. And let's ease into tonight's journey together. Alpha Centauri A is slightly larger and more luminous than the Sun, classified as a G2V star with a mass approximately 1.1 times solar. Alpha Centauri B is smaller and cooler, a K1V star with about 0.9 solar masses. The two orbit each other with a period of roughly 80 years, their separation varying from about 11 astronomical units at closest approach to 36 astronomical units at maximum distance. This is comparable to the range between Saturn and Neptune in our own solar system. The gravitational dance between these two stars creates a complex environment for any planets that might form, with stable orbits possible only very close to one star or very far from both. Proxima Centauri, the third component, lies about 13,000 astronomical units from the central pair, roughly 0.2 light-years. It is a red dwarf, cool and dim, with only about 12% of the Sun's mass. Despite its faintness, Proxima has attracted enormous attention since 2016, when astronomers announced the discovery of Proxima Centauri b, a planet with at least 1.17 Earth masses orbiting within the star's habitable zone. The possibility that a potentially habitable world exists at our cosmic doorstep has driven subsequent observations, though Proxima's violent flaring activity and strong radiation environment cast doubt on the planet's actual habitability. Ground-based observations of the Alpha Centauri system have been extensive. Telescopes in Chile, including the Very Large Telescope and the European Southern Observatory's instruments, have monitored the stars for decades. Spectroscopy has determined their chemical compositions, revealing metallicities similar to the Sun's, which suggests that planet formation should be possible. Radial velocity measurements, tracking the star's motions toward and away from Earth, have searched for the gravitational tugs of orbiting planets. Several candidate planets have been proposed around Alpha Centauri b, though most have been retracted after further analysis revealed instrumental artifacts or stellar activity masquerading as planetary signals. The challenges of observing planets around Alpha Centauri are substantial. The stars are bright, and any planets would be extremely faint in comparison, lost in the glare. Direct imaging requires blocking the starlight with coronagraphs or starshades, but even with these techniques, the contrast ratio between star and planet is daunting. For Earth-like planets in habitable zones, the angular separation from the star is measured in tens of milliseconds, requiring exceptional resolution and stability. Ground-based adaptive optics can partially compensate for atmospheric distortion, but the atmosphere fundamentally limits what can be observed. Space-based observations have offered improvements. The Hubble Space Telescope has examined the system, though its resolution and sensitivity are marginal for detecting small planets. The planned mission concepts, such as the Habitable Exoplanet Observatory and Starshade-equipped space telescopes, aim to directly image planets around Alpha Centauri, but these remain years or decades from realization. Until recently, the detailed structure of the Alpha Centauri system, particularly the presence and characteristics of any planets beyond Proxima b, remained largely unknown. Theoretical models predicted what might be found. Simulations of planet formation around binary stars like Alpha Centauri A and B suggested that terrestrial planets could form in close orbits around either star, within about 3 astronomical units. Beyond this region, the gravitational perturbations from the companion star would destabilize orbits. Gas giants, if they formed, would likely have been scattered or ejected during the system's early evolution. The metallicity of the stars, slightly higher than the Sun's, hinted that solid material was available for planet building. But whether that material coalesced into planets remained an open question. The habitable zone around Alpha Centauri A, the region where liquid water could exist on a planet's surface, extends from roughly 1.2 to 2.1 astronomical units, comparable to the distance between Earth and Mars in our solar system. For Alpha Centauri B, the cooler star, the habitable zone lies closer, from about 0.7 to 1.2 astronomical units. A planet within these zones would receive similar amounts of energy from its star as Earth does from the Sun, making it a candidate for habitability if other conditions, atmosphere, magnetic field, water, were favorable. Proxima Centauri's habitable zone is much closer, between 0.04 and 0.08 astronomical units, because the star is so dim. Proxima b orbits at approximately 0.05 astronomical units, well within this range, completing an orbit every 11.2 days. However, Proxima's proximity and activity pose severe challenges. Red dwarfs like Proxima are known for violent flares, eruptions that can increase their brightness by factors of 10 or more, and release high-energy radiation and charged particles. Proxima b, orbiting so close, would be subjected to this harsh environment. Whether an atmosphere and water could survive, let alone life, is uncertain. The expectations for what the James Webb Space Telescope might find when it observed Alpha Centauri were measured. Webb's infrared capabilities and superior resolution offered the possibility of detecting thermal emission from planets, particularly warm gas giants or super-Earths. Its spectroscopic instruments could potentially characterize planetary atmospheres if planets transited their stars, though the orbital geometries of the Alpha Centauri system made transits unlikely for most configurations. The hope was to confirm or refute previous planet candidates, identify new worlds, and perhaps glimpse the chemical signatures that might hint at habitability. What Webb observed, when its instruments were finally trained on the system in late 2023 and early 2024, did not match these expectations. The data returned contained features that were unanticipated, patterns that did not fit existing models of stellar and planetary systems. The initial analysis was cautious, with researchers checking for instrumental artifacts, calibration errors, or misidentifications. But as the observations were repeated and confirmed, it became clear that Alpha Centauri, the most studied nearby star system, harbored surprises that challenged fundamental assumptions about stellar evolution, planet formation, and the nature of the interstellar environment. The surprises were not a single anomalous reading, but a collection of interrelated findings, each unexpected on its own and collectively forming a picture of the system that was inconsistent with decades of prior understanding. What was thought to be a relatively simple binary system with a distant red dwarf companion revealed itself as a far more complex and dynamic environment. The implications extended beyond Alpha Centauri itself, raising questions about how well astronomers understand even the nearest and most intensively studied stars. This realization marked a turning point. The Alpha Centauri system, long viewed as a nearby analog to help understand solar system formation and a potential target for future interstellar missions, became a case study in the limits of observational astronomy and the dangers of extrapolating from incomplete data. What Webb found inside Alpha Centauri was not what it was supposed to find, and that discrepancy opened a new chapter in the study of our nearest stellar neighbors. The James Webb Space Telescope operates primarily in the infrared portion of the electromagnetic spectrum, observing wavelengths from 0.6 to 28 micrometers. This range, spanning near-infrared through mid-infrared, is ideal for penetrating dust, detecting cool objects, and characterizing thermal emission from planets and circumstellar material. Unlike the Hubble Space Telescope, which observes predominantly in visible and ultraviolet light, Webb is optimized to see what is hidden or faint in optical wavelengths. When pointed at Alpha Centauri, Webb's instruments, the Near-Infrared Camera, NIR-CAM, the Near-Infrared Spectrograph, NIR-SPEC, and the Mid-Infrared Instrument, MIRI, were expected to provide unprecedented detail on the system's structure and any planetary companions. What they revealed instead was a set of observations that did not align with the standard picture of a mature, stable stellar system. The first unexpected finding emerged from NIR-CAM imaging. The camera, capable of resolving fine details and detecting faint sources, captured images of both Alpha Centauri A and B at multiple infrared wavelengths. The stars themselves appeared as expected, bright point sources with diffraction patterns characteristic of Webb's hexagonal mirror segments. But surrounding the stars, particularly Alpha Centauri A, was a faint extended emission that had not been seen in previous observations. This emission was not uniform, but showed structure, hints of clumps and filaments extending outward from the star. Initially, researchers suspected this was scattered light, photons from the star reflecting off dust grains in the interstellar medium or residual material from the system's formation. Mature stars like Alpha Centauri A, roughly 5 to 6 billion years old, should have cleared their surrounding environments of most primordial dust through radiation pressure and stellar wind. Debris disks, belts of material analogous to our asteroid belt or Kuiper belt, can persist, but they are typically cold and faint, detectable primarily through infrared excess at longer wavelengths. The emission Webb detected was neither consistent with a simple debris disk nor with scattered interstellar light. Its brightness and spatial distribution suggested something more substantial. Spectroscopic analysis using NIR-SPEC provided additional clues. By dispersing the light from the extended emission into its component wavelengths, astronomers could identify the chemical fingerprints of the material. The spectrum showed absorption and emission features consistent with silicate dust, small grains of minerals similar to those found in comets and asteroids. But there were also unexpected features, emission lines from ionized gas, including hydrogen, oxygen, and carbon. The presence of ionized gas suggested that the material was being heated and energized, possibly by radiation from the star or by some other mechanism. The temperature of the dust, inferred from its thermal emission, was also surprising. Dust grains in a debris disk typically have temperatures determined by their distance from the star and the amount of starlight they absorb. For Alpha Centauri A, dust at a few astronomical units should have temperatures of a few hundred Kelvin, warm but not hot. The dust Webb observed was warmer than expected, approaching 500 to 700 Kelvin in some regions. This elevated temperature implied that the dust was either closer to the star than initially thought, or being heated by additional energy sources beyond stellar radiation. MIRI observations, probing longer infrared wavelengths, added another layer of complexity. At wavelengths around 10 to 20 micrometers, MIRI detected thermal emission consistent with cooler dust at larger distances, as expected for a debris disk. But it also revealed a faint, diffuse glow that extended far beyond the immediate vicinity of the stars, reaching tens of astronomical units. This glow was asymmetric, brighter on one side of the system than the other, suggesting an external influence or a dynamic process redistributing material. The asymmetry was particularly puzzling. In a stable, isolated binary system, any disk or cloud of material should eventually settle into a symmetric distribution, either circumbinary, surrounding both stars, or circumstellar, surrounding one star individually. Asymmetries can arise from planetary perturbations, interactions with the companion star, or external forces such as interstellar wind. But the degree of asymmetry Webb observed was more pronounced than simple planetary perturbations could explain. It suggested that material was being displaced or replenished in ways that were not accounted for in existing models. Another unexpected observation involved Proxima Centauri. Although Proxima is a separate system, orbiting the Alpha Centauri AB pair at a vast distance, Webb's wide field of view and sensitivity allowed simultaneous observations of all three stars. MIRI detected faint infrared emission in the space between Proxima and the central binary, material that appeared to be associated with Proxima but extended in the direction of Alpha Centauri A and B. This suggested a possible connection, a tenuous bridge of gas or dust linking the red dwarf to its distant companions. Such a connection was not predicted. At 13,000 astronomical units separation, the gravitational influence of the central binary on Proxima is weak, and any material escaping from Proxima should disperse into the interstellar medium rather than streaming toward Alpha Centauri AB. The detection of this bridge hinted at either a temporary phenomenon, perhaps material ejected by a recent flare event on Proxima, or a more persistent interaction mediated by magnetic fields or stellar winds. Proxima itself revealed additional surprises. NIR-spec observations captured the star during a flare, a brief eruption that increased its infrared brightness by a factor of several within minutes. The spectrum during the flare showed strong emission lines from highly ionized species, indicating temperatures of tens of thousands of Kelvin in the flare plasma. This was expected. Proxima is known for violent activity, but the flare also produced a burst of mid-infrared emission detected by MIRI, suggesting that dust or solid particles were being heated or vaporized by the flare's energy. The presence of dust so close to Proxima, within the region affected by flares, was unexpected. Dust should be destroyed or blown away by the star's activity, yet it appeared to persist. The combination of these observations, extended emission around Alpha Centauri A, ionized gas, warmer than expected dust, asymmetric distribution, a possible material bridge to Proxima, and dust surviving near Proxima, despite flares, painted a picture of the Alpha Centauri system that was far more dynamic and complex than anticipated. Mature stellar systems are supposed to be quiescent environments, with planets in stable orbits and residual dust slowly eroding under radiation pressure. What Webb observed suggested ongoing activity, material being heated, ionized, and redistributed by processes that were not immediately obvious. The initial interpretations were tentative. One possibility was that the system had recently experienced a collision or disruptive event, such as the breakup of a comet or the collision of asteroids, releasing fresh dust and gas. Such events are rare in mature systems, but not impossible. Observations of other stars, such as Beta Pictoris, have revealed episodic dust production from collisional cascades. But the scale and distribution of the material in Alpha Centauri seemed too extensive for a single recent event. Another possibility was that the system harbored undetected planets whose gravitational influence was stirring up debris or maintaining material in unstable orbits. A planet on an eccentric orbit could periodically pass through a debris belt, scattering material and creating transient asymmetries. However, the required planetary mass and orbit would need to be finely tuned to produce the observed effects without being detected in previous radial velocity surveys. A third interpretation involved interactions with the interstellar medium. Stars move through space, and their motion through the diffuse gas between stars can create bow shocks or tail structures as stellar wind interacts with interstellar material. Alpha Centauri's velocity relative to the local interstellar medium is modest, about 25 kilometers per second, which should not produce dramatic effects. But local variations in interstellar density or magnetic field could create asymmetries. None of these explanations fully accounted for all the observations: the extended emission, the ionized gas, the warm dust, the asymmetry, and the Proxima connection each required separate hypotheses, and finding a single coherent model that explained everything proved elusive. The data suggested that something was happening in the Alpha Centauri system that was not captured by the standard model of a passive, evolved binary with a distant red dwarf companion. As researchers worked to understand the Webb observations, a pattern began to emerge. The unexpected features were not random anomalies. but showed correlations in space and time. Regions with warmer dust coincided with stronger ionized gas emission. The asymmetry in the disk aligned with the direction of Proxima Centauri. The material bridge appeared to connect regions of recent activity. These correlations hinted that the various phenomena were related, driven by a common underlying process. This realization shifted the investigation from cataloging individual anomalies to searching for a unifying explanation. What could produce warm dust, ionized gas, asymmetric distribution, and connections between Proxima and the central binary simultaneously? The answer, when it began to take shape through follow-up observations and detailed modeling, was not what anyone had predicted. It involved processes that were thought to occur primarily in younger systems or in more extreme environments, not in mature, sun-like stars at humanity's doorstep. What Webb's infrared eyes revealed was that proximity does not guarantee understanding. The Alpha Centauri system, observed for over a century and studied with every available technique, had been hiding complexity that only the unprecedented sensitivity and resolution of infrared space-based instruments could expose. The surprises were not errors in the data, but genuine discoveries, and they demanded explanation. The question was not whether the observations were real, but what they meant for our understanding of stellar systems, planet formation, and the environments in which life might arise. Debris disks are common around mature stars, remnants of planet formation consisting of dust, ice, and rocky fragments. Our own solar system has two prominent examples: the asteroid belt between Mars and Jupiter, and the Kuiper belt beyond Neptune. These structures represent material that never coalesced into planets, along with debris from collisions between larger bodies. Over billions of years, radiation pressure, stellar wind, and collisions grind the material down, causing the disks to fade. By the time a star system reaches the age of Alpha Centauri, roughly 5 to 6 billion years, debris disks should be faint and relatively devoid of small dust grains, which are efficiently removed by radiation pressure. What Webb observed around Alpha Centauri A defied this expectation, revealing a debris disk that was not only present, but surprisingly bright and rich in fine dust. The disk's brightness in mid-infrared wavelengths exceeded predictions based on the star's age and metallicity. Models of debris disk evolution account for the gradual loss of dust through various processes. Small particles, those smaller than a micrometer, are expelled by radiation pressure on timescales of hundreds to thousands of years. Larger particles, millimeters to meters in size, collide and fragment, producing smaller debris that is then expelled. This collisional cascade steadily depletes the disk's mass over time. After several billion years, only a faint remnant should remain, detectable primarily through subtle infrared excess at long wavelengths. Alpha Centauri A's disk did not fit this profile. MIRI observations showed infrared excess, indicating the presence of substantial amounts of dust at temperatures consistent with locations between 1 and 10 astronomical units from the star, roughly the region between Earth and Saturn in our solar system. The amount of dust inferred from the brightness implied a total mass of fine particles, far exceeding what should remain after billions of years of collisional evolution. Either the disk was being continuously replenished, or the standard models of debris disk depletion were incorrect for this system. Replenishment requires a source. In younger systems, comets and asteroids are abundant, and collisions between them produce fresh dust. But in a mature system like Alpha Centauri, the population of small bodies should have been depleted. Planets, if present, can stir the debris and trigger collisions, but this process becomes less efficient over time as the remaining bodies are ground down or ejected. The brightness of Alpha Centauri A's disk suggested a level of collisional activity that was inconsistent with the expected population of planetesimals in an old system. One hypothesis was that a recent catastrophic collision, perhaps between two large asteroids or a comet and an asteroid, had injected a large amount of fresh dust into the disk. Such events are stochastic, occurring at unpredictable intervals, and could temporarily brighten a debris disk. Observations of other stars have captured systems in the aftermath of such collisions, showing transient spikes in infrared brightness that fade over years to decades as the dust is expelled. However, the spatial distribution and temperature profile of Alpha Centauri A's disk did not match the expected signature of a single recent collision. The dust appeared to be spread across a range of distances, not concentrated in a narrow ring, as would result from a localized impact. Another possibility involved the gravitational influence of planets. If Alpha Centauri A hosts one or more planets on eccentric orbits, their gravitational perturbations could maintain a population of asteroids in unstable orbits, leading to ongoing collisions. The planets themselves would act as dynamical stirrers, pumping up the eccentricities of smaller bodies and increasing collision rates. This mechanism can sustain debris production over long timescales, though it requires specific planetary masses and orbits. No planets around Alpha Centauri A had been confirmed, but the presence of a debris disk rich in dust could be indirect evidence for their existence. The composition of the dust provided additional clues. NERSpec's spectroscopic observations revealed absorption features consistent with silicate minerals, similar to those found in comets and asteroids in our solar system. This was expected, but there were also subtle features suggesting the presence of water ice and organic compounds, materials that are typically found in the outer regions of planetary systems, where temperatures are low enough for volatiles to condense. The detection of icy material in Alpha Centauri A's disk was surprising, because the dust appeared to be warm, with temperatures too high for water ice to survive unless it was freshly produced or shielded from direct starlight. This suggested that the dust might be originating from comets, icy bodies that release dust as they approach the star and their ice sublimates. Cometary activity could explain the presence of both silicates and ice signatures, as well as the warm temperatures if the dust was concentrated near the sublimation zone where comets are most active. However, in a mature system, the population of comets should be largely depleted, either ejected by planetary perturbations or consumed by the star over billions of orbits. The persistence of active comets in Alpha Centauri A's inner system required explanation. Another anomaly involved the spatial distribution of the dust. Instead of forming a smooth, symmetric disk, the dust showed clumps and asymmetries. MIRI images revealed brighter regions and fainter gaps, suggesting that the disk was structured by gravitational forces. In systems with planets, the gravitational influence of the planets creates gaps in the disk, where their orbits clear out material, and resonances can produce clumps where material accumulates. The structures in Alpha Centauri A's disk were consistent with planetary perturbations, but inferring specific planetary masses and orbits from disk morphology is challenging. Multiple configurations could produce similar patterns. The asymmetry extended beyond simple clumping. One side of the disk appeared brighter and more extended than the opposite side, creating a lopsided appearance. This asymmetry could result from a planet on an eccentric orbit, which would compress the disk on one side during its closest approach and rarefy it on the other. Alternatively, the asymmetry might indicate external influences, such as interactions with Alpha Centauri b, the companion star. Although Alpha Centauri b orbits at distances ranging from 11 to 36 astronomical units, its gravitational pull could affect material at the outer edges of Alpha Centauri A's debris disk, creating tidal distortions. The interaction between the two stars in the binary system has long been recognized as a complicating factor for planet formation and stability. During closest approach, Alpha Centauri b passes within the region where a debris disk around Alpha Centauri A might extend. This periodic perturbation could destabilize orbits, triggering collisions and injecting material into the inner system. The 80-year orbital period of the binary means that such events occur regularly on astronomical timescales, potentially sustaining debris production over the system's lifetime. However, modeling these interactions in detail requires understanding the precise orbital elements of any planets and the structure of the debris populations, neither of which was well constrained. The Webb observations provided evidence for structure and activity, but did not directly reveal the underlying causes. The debris disk that shouldn't exist, according to conventional models, was clearly present. The challenge was determining why it existed and what it revealed about the hidden architecture of the Alpha Centauri system. One implication was that Alpha Centauri A might be more dynamically active than previously assumed. Instead of a settled system with planets in stable circular orbits and a quiescent disk of leftover debris, the system might be in a state of ongoing evolution, with planets migrating, debris being replenished, and material being redistributed by gravitational interactions. This would have significant consequences for any planets in the habitable zone. A dynamically active system increases the risk of impacts, as asteroids and comets are scattered into the inner regions. High impact rates could threaten the stability of atmospheres and the survival of life. Conversely, moderate levels of debris delivery could be beneficial, providing water and organic compounds to terrestrial planets. Earth's oceans and the organic molecules necessary for life may have been delivered in part by comets and asteroids. A balance between too little and too much impact activity might create favorable conditions for habitability. The question was whether Alpha Centauri A's disk represented a benign level of activity or a hazardous bombardment environment. The debris disk also affected the prospects for direct imaging of planets. Dust scatters starlight, creating a background glow that makes faint planets harder to detect. The brightness of Alpha Centauri A's disk in infrared wavelengths meant that any attempt to image planets around the star would have to contend with this additional source of emission. Techniques such as coronagraphy and advanced image processing could mitigate the effect, but the disk added complexity to an already challenging observation. What the debris disk revealed was that Alpha Centauri A, far from being a simple analog to the Sun in its middle age, was a system with active processes that were not fully understood. The disk's existence and properties demanded the presence of mechanisms replenishing dust, stirring orbits, and maintaining structure. Those mechanisms, whether planets, comets, or interactions with Alpha Centauri B, were not directly observable but left fingerprints in the disk's morphology and spectrum. Understanding the disk was essential to understanding the system as a whole, and the Webb observations had opened a window into this hidden complexity. Beyond the unexpected debris disk, Webb's observations revealed another anomaly within the Alpha Centauri system, an excess of warm emission originating from the inner regions, closer to the stars than any previously detected material. This emission, detected by both NIRCam and MIRI, corresponded to temperatures between 700 and 1200 Kelvin, far warmer than the dust in the debris disk and consistent with material located within the first astronomical unit around Alpha Centauri A. At these distances, temperatures are high enough that most volatile materials would be vaporized, leaving only refractory minerals and metals. The presence of substantial warm material so close to the star raised immediate questions. What was it? Where did it come from? And what did it imply about the inner architecture of the system? Thermal emission at these temperatures typically arises from hot dust or rocky surfaces heated by proximity to a star. In the solar system, Mercury's surface reaches temperatures around 700 Kelvin on its sunlit side, and dust particles orbiting close to the Sun can achieve similar temperatures. The emission Webb detected from Alpha Centauri A's inner region was consistent with a population of dust grains or rocky bodies within a fraction of an astronomical unit from the star, a region analogous to the orbit of Mercury or even closer. The amount of emission, however, was higher than expected, for a simple analogy to Mercury or scattered dust. Modeling the thermal properties required either a large mass of material, substantially more than a single planet could represent, or a configuration that maximized the surface area exposed to starlight, such as a disk or ring of particles. The emission's brightness and temperature profile did not match the signature of a single rocky planet. Instead, it suggested an extended population of warm material, perhaps a dense inner disk, or a swarm of small bodies. This raised a fundamental question: how could such material persist? Dust grains close to a star are subjected to intense radiation pressure, which can expel them from the system on timescales of years to centuries. Additionally, the Poynting-Robertson effect, a drag force caused by the absorption and re-emission of starlight, causes dust particles to spiral inward toward the star, where they are ultimately vaporized. In a mature system like Alpha Centauri, any primordial dust in the inner region should have been removed billions of years ago. The presence of warm dust implied ongoing production or replenishment. One mechanism for producing inner system dust is the evaporation of comets. Comets that venture into the inner regions of a stellar system sublimate, releasing gas and dust. Some of this dust can linger temporarily before being expelled or vaporized. However, in a system as old as Alpha Centauri, the population of comets on sun-grazing orbits should be largely depleted. The sustained presence of warm inner dust suggested that comets were continuously being perturbed into the inner system, requiring a mechanism to replenish the population. Another possibility was collisional production. If a population of asteroids, or rocky planetesimals, orbits close to the star, collisions between them would generate dust. The dust would be heated by the star's radiation and would produce the observed thermal emission. For this mechanism to sustain the observed brightness, collision rates would need to be high, implying a dynamically active inner system. Such activity could be driven by gravitational perturbations from planets, either within the inner system or on more distant orbits. The spectroscopic data from NIRSpec provided hints about composition. The warm emission showed features consistent with silicate minerals, similar to the debris disk, but with differences suggesting higher temperatures and possibly partial melting or vaporization. There were also indications of metallic components, such as iron and magnesium, which are abundant in rocky bodies and would be exposed if silicate dust was being heated to temperatures approaching vaporization. This composition was consistent with material derived from asteroids or rocky planets rather than comets, which would show stronger signatures of volatiles. Another striking feature was the spatial distribution. The warm emission was not evenly distributed around Alpha Centauri A, but showed concentration towards certain regions. This asymmetry suggested structure within the inner system, possibly a dense ring or clump of material at specific orbital distances. Rings can form through resonances with planets, where gravitational interactions concentrate material at preferred locations. The detection of a structured inner disk would imply the presence of at least one planet shepherding the material. The temperatures inferred from the emission also varied with location. Some regions showed temperatures exceeding 1000 Kelvin, while others were cooler, around 700 to 800 Kelvin. This variation indicated that the material was distributed across a range of distances from the star, with closer material hotter and more distant material cooler. Mapping this temperature gradient allowed researchers to estimate the radial extent of the warm region, which appeared to span from roughly 0.1 to 0.5 astronomical units. This range is significant because it overlaps with the region where terrestrial planets might form. In our solar system, the terrestrial planets, Mercury, Venus, Earth, and Mars, all formed within 1.5 astronomical units of the Sun. If Alpha Centauri A has a similar population of inner rocky bodies, the warm emission could be a signature of an inner planetary system. However, distinguishing between a disk of dust and debris and one or more actual planets requires more detailed observations. One possibility explored by researchers was that the warm emission originated from a single large body, a rocky planet or dwarf planet, with a surface heated by the star. A planet with a radius comparable to Earth or smaller, located at 0.2 to 0.3 astronomical units, could produce thermal emission consistent with the observations. However, such a planet would need to have a surface largely devoid of atmosphere to reach the observed temperatures, as atmospheres redistribute heat and lower dayside temperatures. A bare rock world, similar to Mercury, could fit. The challenge with this interpretation was that a single planet would produce a point source of emission, not the extended structure observed. Unless the planet had an extensive dust cloud or debris ring surrounding it, perhaps generated by impacts or volcanic activity, it could not account for the spatial distribution of the warm emission. Some models invoked a planet with a dust ring, similar to Saturn, but much closer to its star, and composed of rocky rather than icy particles. Such a system was unprecedented, but not physically impossible. Another scenario involved multiple small bodies, a population of asteroids or planetesimals in the inner system. If these bodies were numerous and closely packed, their collective thermal emission could mimic an extended disk. Collisions between them would produce dust, replenishing the population and maintaining the observed brightness. The gravitational interactions among the bodies and with any planets could prevent them from coalescing into a single large planet, keeping the system in a state of arrested growth. The presence of warm material in the inner region also had implications for planetary habitability. If the inner system of Alpha Centauri A is filled with debris, any planets in the habitable zone, located at roughly 1.2 to 2.1 astronomical units, might experience frequent impacts from asteroids and comets scattered outward by the inner debris. High impact rates could strip atmospheres, sterilize surfaces, and create inhospitable conditions. Conversely, if the inner system's activity was driven by the presence of planets that have cleared their immediate surroundings, the habitable zone might be relatively stable and protected. The mystery of the warm inner region was compounded by the lack of direct detections. No planet had been confirmed around Alpha Centauri A, despite extensive radial velocity searches. The warm emission provided indirect evidence for material in the inner system, but it did not definitively reveal whether that material was in the form of planets, asteroids, dust, or some combination. Resolving this ambiguity required follow-up observations with higher resolution and sensitivity, possibly using Webb's coronagraphic modes to block the starlight and directly image the inner system. What the warm inner region revealed was that Alpha Centauri A's environment did not match the expectations for a mature, settled system. The presence of substantial warm material, whether dusty debris or rocky bodies, indicated ongoing dynamic processes. The inner system was not a quiet, stable environment, but one where material was being heated, redistributed, and possibly consumed. Understanding what was happening in this region was essential for assessing the potential for planets and life in the Alpha Centauri system. The combination of the debris disk and the warm inner region painted a picture of a system that was more complex than anticipated. Material was present at multiple radial distances, with different temperatures. The combination of the debris disk and the warm inner region painted a picture of a system that was more complex than anticipated. Material was present at multiple radial distances, with different temperatures, compositions, and dynamical states. This suggested a hierarchical structure, with distinct populations of dust and debris at different locations, each shaped by different physical processes. The challenge was to construct a coherent model that explained all these features simultaneously, and that model remained elusive as researchers worked through the Webb data. Among the most perplexing features in Webb's observations of Alpha Centauri was the detection of ionized gas distributed throughout the inner system. Spectroscopic data from NIRSpec revealed emission lines from highly ionized atoms, including oxygen, carbon, and nitrogen, with ionization states indicating temperatures of tens of thousands of Kelvin or exposure to high-energy ultraviolet and X-ray radiation. In a mature stellar system around Sun-like stars, ionized gas at these levels should not exist. The radiation environment near stars like Alpha Centauri A and B is far too gentle to produce significant ionization of circumstellar material. The presence of this gas suggested either an unexpected radiation source or a process injecting energy into the system's material in ways that were not accounted for in standard models. Ionized gas is common in certain astrophysical contexts. Around young stars, intense ultraviolet radiation ionizes surrounding gas clouds, creating emission nebulae. Around massive stars, stellar winds and radiation create vast ionized regions. In active galactic nuclei or X-ray binaries, extreme radiation fields ionize gas across large volumes. But Alpha Centauri A and B are middle-aged Sun-like stars, Their ultraviolet output is moderate, and their X-ray emission is low compared to more active stars. They should not produce ionization strong enough to explain the observed emission lines. The emission lines detected by NIR spec were characteristic of forbidden transitions, quantum mechanical processes that occur in low-density gas when atoms are excited by collisions or radiation. These lines are commonly seen in planetary nebulae, supernova remnants, and other environments where gas is ionized and then allowed to cool slowly. Their presence around Alpha Centauri indicated that the gas was not only ionized, but also relatively diffuse, with densities low enough that forbidden transitions could occur. The spatial distribution of the ionized gas added to the mystery. It was not concentrated near the stars, where stellar radiation would be strongest, but appeared to be spread throughout the inner and middle regions of the system, extending to several astronomical units. Some of the strongest emission came from regions coinciding with the debris disk and warm inner material, suggesting a connection between the dust and the ionized gas. This correlation implied that the ionization was linked to the presence of solid material, perhaps through interactions between gas and dust or through localized heating events. One hypothesis was that the ionization resulted from shock heating. If material in the system was colliding at high velocities, the kinetic energy of the collisions could heat gas to temperatures sufficient for ionization. Shock waves, produced when fast-moving material slams into slower material, can reach temperatures of tens of thousands of Kelvin. In planetary systems, such shocks might occur during impacts between asteroids, during the evaporation of comets passing close to the star, or in interactions between debris and any planetary atmospheres. For shock heating to explain the observed ionization, collision velocities would need to be substantial, typically tens of kilometers per second or more. Orbital velocities in the inner Alpha Centauri system are on the order of 30 to 50 kilometers per second, depending on distance from the star. Collisions between bodies on intersecting orbits could easily reach these velocities. If the system is experiencing a high rate of collisions due to dynamical stirring, shock-heated gas would be continuously produced. However, this gas would cool and recombine on timescales of hours to days, requiring sustained collision activity to maintain the observed emission. Another possibility involved the evaporation of comets or volatile-rich asteroids. As these bodies approach the star, their ices sublimate, releasing gas. If the gas is released rapidly, or if the body is moving quickly, the expanding gas can form a shock with the surrounding material or the stellar wind. Additionally, ultraviolet radiation from the star can ionize the gas, particularly if the gas contains elements like carbon and oxygen that ionize more easily. Cometary evaporation could explain the presence of ionized gas in the inner system, but it required a substantial population of active comets, more than would typically exist in a mature system. Stellar wind interactions provided another potential mechanism. All stars emit stellar winds, streams of charged particles flowing outward from the star. The Sun's solar wind, for example, carries ionized hydrogen and helium throughout the solar system. If Alpha Centauri A's stellar wind interacts with gas released from comets, asteroids, or planets, it could compress and heat the gas, producing ionization. However, the stellar wind from a star like Alpha Centauri A is relatively weak, and interactions with circumstellar material typically produce only modest heating unless the material is very dense or moving very fast. The presence of ionized nitrogen was particularly intriguing. Nitrogen is difficult to ionize compared to hydrogen or oxygen. It requires higher energy photons or hotter temperatures. The detection of ionized nitrogen suggested that the ionization mechanism was efficient and energetic. This pointed toward either a very hot process, such as shock heating at high velocities, or the presence of a strong source of high-energy photons, such as extreme ultraviolet or soft X-rays. Alpha Centauri A's X-ray emission, while measurable, is not exceptionally strong. Observations by X-ray telescopes like Chandra have shown that the star emits X-rays at levels comparable to the Sun during solar maximum, but this is far below what would be needed to ionize large amounts of gas at several astronomical units distance. Unless there were transient X-ray brightening events, similar to solar flares but more intense, the stellar X-ray output alone could not explain the ionization. This led to speculation about unseen sources. If the system harbored a planet with a magnetic field and an atmosphere, interactions between the planet's magnetosphere and the stellar wind could accelerate particles to high energies, producing localized X-ray emission. Jupiter's magnetosphere, for instance, generates auroral X-rays through particle acceleration. A similar process at Alpha Centauri, scaled up by a more intense stellar wind or a more massive planet, could contribute to ionizing nearby gas. However, this would require specific planetary properties and configurations that remained unconfirmed. Another consideration involved the binary nature of the system. Alpha Centauri b, though cooler than Alpha Centauri a, also emits radiation and has its own stellar wind. During the binary's periastron, when the two stars are closest, interactions between their winds and magnetic fields could create regions of enhanced heating and particle acceleration. These interaction regions might produce localized ionization, which could then mix and disperse throughout the system over the course of the binary's 80-year orbit. However, modeling such interactions in detail required understanding the magnetic field strengths and stellar wind properties of both stars, neither of which was well constrained. The ionized gas also raised questions about the chemical evolution of the system. Gas in a planetary system is typically primordial, left over from the protoplanetary disk, or secondary, released by comets, asteroids, or planetary outgassing. The presence of ionized gas with detectable amounts of carbon, nitrogen, and oxygen suggested that at least some of the gas was enriched in heavy elements, consistent with a secondary origin. This implied ongoing degassing or evaporation of solid bodies, replenishing the gas that would otherwise be lost to stellar wind or photoevaporation. The temporal behavior of the ionized gas provided additional clues. Follow-up observations, conducted months after the initial Webb data, showed variations in the strength of some emission lines. These variations suggested that the ionization was not constant but fluctuated over time, possibly in response to discrete events such as collisions, flares, or changes in stellar activity. Monitoring the system over longer periods could reveal whether the ionization was episodic or sustained, and whether it correlated with the orbital phases of the binary or other periodic phenomena. What the ionized gas revealed was that the Alpha Centauri system was not in a passive, steady state. Energy was being deposited into the circumstellar material, ionizing gas and heating it to temperatures far exceeding equilibrium values for simple stellar radiation. The mechanisms responsible, whether shock heating from collisions, interactions with stellar winds, or unanticipated radiation sources, indicated that the system was dynamically active on timescales ranging from hours to years. This activity had profound implications for understanding the environment in which any planets might exist, and the potential for those planets to support atmospheres, and by extension, life. Proxima Centauri, the red dwarf orbiting at a vast distance from Alpha Centauri, A and B, was not expected to play a significant role in Webb's observations of the central binary. At 13,000 astronomical units separation, roughly 0.2 light-years, Proxima is gravitationally bound to the system, but effectively isolated, evolving independently. Yet Webb's data revealed features suggesting a connection between Proxima and the central pair, a tenuous bridge of material and energy that should not exist according to conventional understanding. This unexpected connection challenged assumptions about how widely separated components of multiple star systems interact, and hinted at processes operating on scales far larger than anticipated. The first indication of the connection came from MIRI's wide-field imaging. When observing the central binary, MIRI's detectors, which cover a broader field of view than NeoCam, captured faint infrared emission extending from the region around Proxima Centauri toward Alpha Centauri A and B. This emission was extremely faint, near the detection limit, but its spatial pattern was consistent with a filamentary structure stretching across thousands of astronomical units. The emission's temperature, inferred from its spectral characteristics, was cold, only a few tens of Kelvin, indicating that it consisted of dust or gas far from any heat source. Cold material in the interstellar medium is not unusual. The space between stars contains diffuse clouds of gas and dust at temperatures ranging from 10 to 100 Kelvin. However, the emission Webb detected was not randomly distributed interstellar material. Its orientation, aligned roughly along the line connecting Proxima to the Alpha Centauri binary, and its faint concentration suggested it was associated with the stellar system rather than coincidental foreground or background material. Spectroscopic observations using NIR spec targeted regions along the filament, though sensitivity was limited by the faintness of the emission. The spectra showed absorption features consistent with molecular hydrogen and carbon monoxide, molecules that form in cold, dense gas. These features confirmed that the emission was indeed from molecular material, not just scattered light or instrumental artifacts. The presence of molecules indicated densities higher than typical interstellar space, suggesting that the material had originated from one of the stars rather than from the surrounding medium. One possibility was that the material represented a stellar wind outflow from Proxima Centauri. Red dwarfs like Proxima emit stellar winds, though generally weaker than the Sun's solar wind. Over time, wind material disperses into space, but if Proxima's wind has been blowing for billions of years, it could have created an extended envelope of gas around the star. The alignment of the detected filament toward Alpha Centauri A and B could be coincidental or could reflect the influence of the binary's gravity or radiation pressure, shaping the wind's dispersion. However, stellar wind from a red dwarf should disperse roughly isotropically, unless influenced by external forces. The fact that the emission appeared more concentrated in the direction of the central binary suggested an interaction. One mechanism for such interaction is ram pressure. As Proxima orbits the Alpha Centauri binary over millions of years, its motion through the residual gas and dust surrounding the binary could create a bow shock or tail structure, similar to how the Sun's motion through the interstellar medium creates a heliotail. The velocities involved are small, only a few kilometers per second, but over long timescales, even modest ram pressure can shape gas distributions. Another possibility involved magnetic fields. Stars possess magnetic fields that extend into space, carried by stellar winds. If Proxima's magnetic field and the magnetic fields of Alpha Centauri A and B are aligned or interact, they could channel particles and gas along field lines, creating filamentary structures. Magnetic reconnection events, where field lines break and reconfigure, can accelerate particles and heat gas, producing detectable emission. This mechanism operates in the Sun's magnetosphere and has been observed in binary star systems, but it is typically associated with stars in much closer orbits than Proxima's. The detection of ionized gas along the filament added another layer of complexity. NIR spectra showed faint emission lines from ionized hydrogen and other elements, indicating that at least some of the gas was not only cold and molecular, but also partially ionized. This ionization was unexpected. The radiation fields from Proxima and the central binary, at the distances involved, should be too weak to ionize gas significantly. The presence of ionization suggested either that the gas was being heated by shocks or that there were localized regions of enhanced radiation. One scenario involved flare activity on Proxima Centauri. Proxima is known for frequent and intense flares, eruptions that increase its brightness by factors of several and release bursts of high-energy radiation and particles. During a major flare, Proxima's X-ray and ultraviolet output can spike dramatically. If a flare ejects material, either as a coronal mass ejection or through enhanced stellar wind, and if that material travels outward along the filament toward the central binary, it could carry ionized gas and energetic particles across the intervening space. This ejection process, if real, would operate on timescales of years to decades, as the material would travel at stellar wind velocities of hundreds of kilometers per second and cover distances of tens of thousands of astronomical units. Webb's observations, capturing a snapshot in time, might be detecting material from a flare that occurred years or even decades earlier. now dispersed and cooled, but still detectable. Follow-up observations monitoring Proxima's flare activity and correlating it with changes in the filament's brightness could test this hypothesis. Another intriguing aspect was the potential for material exchange. If gas and dust are flowing from Proxima toward the central binary, this material could eventually mix with the debris disk and inner system material around Alpha Centauri A and B. This would introduce chemically distinct material, possibly enriched in elements processed through Proxima's stellar evolution, into the central system. Such exchange could affect the composition of any planets forming or existing around the binary, and could influence the chemical signatures detected in the debris disk and warm inner region. Conversely, material could flow in the opposite direction, from the central binary toward Proxima. The stellar winds from Alpha Centauri A and B are stronger than Proxima's, and over time, they could push gas and dust outward. If this material reaches Proxima, it could interact with the red dwarf's magnetosphere or be swept up by its stellar wind, creating observable effects. This bidirectional exchange, if occurring, would make the Alpha Centauri system a more interconnected entity than previously recognized. The gravitational influence of Proxima on the central binary, while weak, is not zero. Over the system's 5 to 6 billion year lifetime, Proxima's gravity could have perturbed the orbits of comets and asteroids in the outer regions of the Alpha Centauri AB system, occasionally scattering them inward toward the stars or outward into interstellar space. This could contribute to the replenishment of the debris disk and the collisional activity inferred from the warm inner emission. In this sense, Proxima might play an indirect but significant role in shaping the environment around the central binary. The connection between Proxima and the central binary, if confirmed through additional observations, would redefine how astronomers think about wide binary and multiple star systems. Traditionally, components separated by thousands of astronomical units are treated as independent, interacting only through their mutual gravitational orbit. Webb's data suggested that even at such vast separations, stars can influence each other through radiation, magnetic fields, and material exchange. This has implications for understanding the formation and evolution of planets in multiple star systems, which comprise a significant fraction of all stellar systems in the galaxy. For the search for habitable planets, the connection introduced both opportunities and challenges. Material exchange could deliver water, organic compounds, and other volatiles between the components of the system, potentially enriching planets around one star with material from another. This could enhance habitability prospects. Conversely, energetic processes associated with the connection, such as flare-driven particle ejections or shock heating, could threaten planetary atmospheres and surface conditions, reducing habitability. What Proxima's unexpected connection revealed was that the Alpha Centauri system was not 3 isolated stars, but a coupled system with interactions spanning light months of space. The boundaries between the components were not clean separations, but blurred zones where material, energy, and magnetic fields could flow and intermingle. Understanding this extended system required thinking beyond individual stars and their immediate environments to consider the system as a whole, a complex, multi-scale structure shaped by processes operating from the surfaces of the stars to the vast spaces between them. The accumulation of observations from Webb, the debris disk, the warm inner region, the ionized gas, and the material bridge to Proxima all pointed toward a common conclusion. The Alpha Centauri system harbored one or more planets that had not been directly detected. Each anomaly could, in principle, be explained by mechanisms not involving planets, but the clustering of multiple independent lines of evidence suggested that planets were the most parsimonious explanation. The challenge was to infer the properties, masses, orbits, and number of these unseen bodies from the indirect signatures they left in the circumstellar environment. Planets exert gravitational influence on everything in their vicinity. They shape debris disks by clearing gaps, creating resonances, and shepherding material into rings and clumps. They stir populations of asteroids and comets, increasing collision rates and producing dust. They can scatter small bodies onto eccentric orbits that bring them close to the star, where they evaporate and release gas. All of these effects were consistent with what Webb observed in the Alpha Centauri system. The structure in the debris disk, particularly the asymmetries and clumps detected by MIRI, was strongly suggestive of planetary perturbations. Models of debris disk dynamics show that a planet on an eccentric orbit will create a lopsided disk, with material concentrated on one side due to gravitational interactions. The degree of asymmetry depends on the planet's mass, eccentricity, and orbital distance. By fitting models to the observed disk morphology, researchers could constrain the possible planetary parameters. Initial modeling efforts suggested that a planet with a mass between 1 and several times that of Earth, orbiting at 1 to 3 astronomical units from Alpha Centauri A, could reproduce the observed asymmetries. The orbit would need to be moderately eccentric, with an eccentricity of 0.1 to 0.3, enough to perturb the disk, but not so extreme as to destabilize it entirely. This placed the hypothetical planet within or near the star's habitable zone, raising immediate interest in its potential for supporting life. However, models are degenerate. Multiple combinations of planetary mass, orbit, and eccentricity can produce similar disk structures. Additionally, the presence of more than one planet would complicate the dynamics, potentially producing features that single-planet models could not capture. Distinguishing between these scenarios required additional data, either more detailed imaging of the disk or direct detection of the planet itself. The warm inner region provided another constraint. The thermal emission from this region, if produced by dust from collisional activity, implied the presence of a population of rocky bodies at 0.1 to 0.5 astronomical units. The existence of such a population could be explained by a planet on an interior orbit, closer than 0.5 astronomical units, whose gravity stirs the debris and prevents it from settling or coalescing. Alternatively, the warm emission could come directly from a rocky planet's surface, heated by the star's radiation. Distinguishing between these interpretations required measuring the variability of the warm emission. If the emission came from a single planet, it should vary as the planet orbits, becoming brighter when the heated day side faces Earth and fainter when the night side or unheated hemisphere is visible. If the emission came from a population of small bodies, it should be relatively constant, as the collective thermal output of many objects averages out orbital variations. Webb's observations, conducted at single epochs, did not provide this temporal information, but follow-up monitoring could. The ionized gas added further evidence. If the ionization was produced by shock heating from collisions, a dynamically active system with planets stirring debris would naturally produce such shocks. If the ionization came from interactions between stellar wind and planetary atmospheres or magnetospheres, this required the presence of planets with atmospheres thick enough or magnetic fields strong enough to create observable effects. Either way, the ionized gas was consistent with the presence of planets. Radial velocity surveys of Alpha Centauri A, conducted over many years, had placed upper limits on planetary masses for various orbital periods. These surveys measured the star's motion toward and away from Earth, induced by the gravitational pull of orbiting planets. The lack of detected signals constrained the presence of massive planets on short-period orbits. However, radial velocity sensitivity drops for planets on longer-period orbits and for planets with masses below a few Earth masses, especially when observing a binary system where the stellar motion is already complex. The planetary signals that Webb's observations suggested, Earth-mass planets at 1 to 3 astronomical units, or smaller rocky bodies closer in, were precisely in the regime where radial velocity surveys struggled. A planet with one Earth mass at 2 astronomical units around Alpha Centauri. A would induce a stellar velocity variation of less than 10 centimeters per second, below the detection threshold of most instruments. Only the most precise spectrographs, operated under ideal conditions over many years, could hope to detect such a signal. This created a situation where indirect evidence from Webb pointed toward planets that direct detection methods had not confirmed. The discrepancy was not necessarily a contradiction. It reflected the different sensitivities of the techniques. Radial velocity surveys detected planets through gravitational effects on the star. Webb detected the consequences of planets on their surroundings. The two approaches complemented each other, but in the case of Alpha Centauri, Webb's observations were revealing planets that remained invisible to other methods. Another line of evidence came from the dynamical stability analysis. The presence of a debris disk and warm inner material required that any planets in the system occupy orbits that did not destabilize these structures. N-body simulations, which model the gravitational interactions among stars, planets, and debris over millions of years, could test whether proposed planetary configurations were stable. These simulations showed that certain orbital arrangements, such as a planet in the habitable zone of Alpha Centauri A with a modest eccentricity, could coexist with a debris disk without clearing it entirely or causing runaway instabilities. The binary nature of the Alpha Centauri system imposed additional constraints. The gravitational influence of Alpha Centauri B, orbiting with a period of 80 years, limits the regions where planets can maintain stable orbits. Planets very close to either star, within about 3 astronomical units, are protected by their host star's gravity and can remain stable. Planets in the region between the stars, at distances greater than a few astronomical units from either star, are destabilized by the companion star's perturbations and would be ejected or sent into chaotic orbits over short timescales. This meant that any planets around Alpha Centauri A had to be confined to the inner few astronomical units, precisely the region where Webb's observations detected the debris disk, warm emission, and ionized gas. The number of planets remained uncertain. A single planet might explain some of the observations, but the diversity of features, disk structure, warm inner region, ionized gas, each with different spatial distributions and physical properties, suggested that multiple planets could be present. A system with 2 or 3 terrestrial planets, analogous to the inner solar system's Mercury, Venus, and Earth, could produce a richer set of interactions and observational signatures. What the evidence for unseen planetary bodies revealed was that the Alpha Centauri system was likely not barren, but populated with worlds. These worlds, hidden from direct view by the glare of their stars and the limitations of current detection methods, left fingerprints across the system's structure and dynamics. The task ahead was to transform these fingerprints from suggestive patterns into definitive detections, either through continued Webb observations with refined techniques or through new missions designed specifically to image planets around nearby stars. The discovery of complex structure and unseen planetary candidates around Alpha Centauri A shifted the conversation from whether planets exist to whether any of them could support life. Habitability depends on a confluence of factors: the presence of liquid water, a stable climate, protection from harmful radiation, and a supply of essential chemical elements. The observations from Webb, while not directly detecting habitable conditions, provided constraints on the environment that any planets in the system would experience. Some of these constraints were encouraging. Others raised concerns. Together, they painted a picture of a system where habitability was possible but not guaranteed, a system where the search for life would face unique challenges. The habitable zone around Alpha Centauri A, the region where liquid water could exist on a planet's surface, extends from approximately 1.2 to 2.1 astronomical units. This is based on the star's luminosity and temperature, which are slightly higher than the Sun's. A planet within this zone would receive similar amounts of stellar energy as Earth, allowing surface temperatures to range from freezing to boiling, depending on atmospheric composition and greenhouse effects. The indirect evidence for planets suggested that at least one body might orbit within or near this range, making it a candidate for habitability. However, the presence of a debris disk and ongoing collisional activity introduced complications. A dynamically active system with frequent asteroid and comet impacts would subject any habitable zone planet to bombardment. The impact rate depends on the density of debris and the gravitational dynamics shaping it. If the system is currently experiencing an elevated impact rate, similar to the late heavy bombardment that Earth experienced about 4 billion years ago, planets in the habitable zone could face hazardous conditions. High impact rates have dual effects. On one hand, they deliver water and organic compounds, which are essential for life. Earth's oceans and the prebiotic molecules from which life arose may have been delivered in part by comets and asteroids. A moderate level of impacts could be beneficial, enriching a planet's surface with volatiles. On the other hand, very high impact rates can be destructive, stripping atmospheres through impact erosion, sterilizing surfaces through heat and pressure, and creating global environmental disruptions. The balance between beneficial delivery and catastrophic bombardment is delicate. The presence of ionized gas suggested that the Alpha Centauri system was energetically active, with shocks, stellar wind interactions, or other processes depositing energy into the environment. For a planet with an atmosphere, this could mean enhanced atmospheric loss, particularly if the planet lacks a strong magnetic field to deflect charged particles. Mars, for example, lost much of its atmosphere over billions of years due to solar wind stripping, a process that would be exacerbated in a more energetic environment. Conversely, a planet with a robust magnetic field could protect its atmosphere and create a magnetosphere that shields the surface from harmful radiation. Earth's magnetic field plays a crucial role in maintaining habitability by deflecting solar wind and cosmic rays. Whether planets around Alpha Centauri A would possess magnetic fields depends on their internal structure, rotation rates, and thermal evolution, factors that cannot be directly observed with current technology. The radiation environment near Alpha Centauri A is another consideration. The star's ultraviolet and X-ray output, while moderate compared to young or active stars, still poses risks to surface life on planets without protective atmospheres or ozone layers. However, life on Earth thrives despite exposure to solar UV, protected by the ozone layer and atmospheric absorption. A planet in Alpha Centauri A's habitable zone could, in principle, develop similar protections if it had a sufficient atmosphere. The binary nature of the system introduced additional variables. Alpha Centauri B, although not the host star for the hypothetical habitable zone planet, periodically approaches to within 11 astronomical units during periastron. At this distance, it could influence the planet's climate through tidal heating, subtle but potentially measurable gravitational effects, or by affecting the distribution of small bodies in the system. Some models suggest that the presence of a companion star could stabilize a planet's obliquity, the tilt of its rotation axis, which in turn stabilizes climate over long timescales. Earth's obliquity is stabilized by the Moon, and a binary companion might serve a similar function. The chemical composition of any planets around Alpha Centauri A is another unknown. The star's metallicity, slightly higher than the Sun's, suggests that planet-building material was rich in heavy elements. This could favor the formation of large rocky cores and abundant water if sufficient volatiles were present during planet formation. However, the exact composition depends on the details of the protoplanetary disk, which dissipated billions of years ago and left no direct observational trace. Proxima Centauri's planet Proxima b offered a nearby comparison, but also highlighted challenges. Proxima b orbits within its star's habitable zone and has a minimum mass consistent with a rocky planet. However, Proxima's flare activity and strong radiation environment cast doubt on whether the planet retains an atmosphere or surface water. Observations with Webb and other telescopes have searched for atmospheric signatures, but have not yet confirmed an atmosphere's presence. The difficulties in establishing Proxima b's habitability underscored the challenges facing any planet around active stars. For Alpha Centauri A, the stellar activity is lower than Proxima's, but the system's dynamic environment, as revealed by Webb, introduced different challenges. A planet in the habitable zone would need to navigate a gauntlet of debris, energetic processes, and possibly unstable orbital dynamics influenced by the binary companion. Whether life could arise and persist under these conditions depended on how severe each factor was, and whether the planet possessed mitigating features like a thick atmosphere, strong magnetic field, and geological activity. The search for biosignatures, chemical indicators of life in a planet's atmosphere, would require detecting and analyzing the planet's spectrum, Gases like oxygen, methane, and water vapor, in certain combinations and abundances, could indicate biological processes. Webb has the capability to perform transmission spectroscopy, where it observes starlight filtering through a planet's atmosphere during a transit. But this requires that the planet's orbit be aligned such that it passes in front of its star from Earth's perspective. The probability of such alignment is low for planets at Earth-like distances from Sun-like stars, typically a few %. If the hypothetical planets around Alpha Centauri A do not transit, direct imaging becomes necessary. This involves blocking the star's light with a coronagraph or starshade and capturing the faint, reflected, or emitted light from the planet. Webb was not primarily designed for high-contrast imaging of exoplanets in reflected light, but future missions, such as the Habitable Worlds Observatory planned by NASA, aim to image and characterize potentially habitable planets around nearby stars. Alpha Centauri A would be a prime target for such a mission. Another approach is atmospheric characterization through high-resolution spectroscopy. Ground-based telescopes equipped with adaptive optics and high-resolution spectrographs can detect molecular absorption lines in a planet's atmosphere by observing the star's spectrum as the planet orbits. These techniques have been successfully applied to hot Jupiters and some smaller planets, though extending them to Earth-like planets in habitable zones around Sun-like stars remains at the edge of current capabilities. The implications for the search for life extended beyond technical feasibility. If planets exist around Alpha Centauri A and one or more resides in the habitable zone, humanity would have a nearby target for focused study. At 437 light-years, Alpha Centauri is the only star system within reach of conceivable interstellar probe missions on human timescales. Initiatives like Breakthrough Starshot, which proposes sending laser-propelled nanocraft to Alpha Centauri at 20% light speed, could reach the system in about 20 years. Such probes could perform close-up reconnaissance, imaging planets, analyzing atmospheres and searching for biosignatures in ways that telescopes cannot. What the implications for habitability revealed was that the Alpha Centauri system, far from being a simple, settled environment, was a complex and dynamic setting where the prospects for life depended on a delicate balance of factors. The system's structure, as unveiled by Webb, suggested that habitability was neither impossible nor assured. It was contingent, dependent on details that remained hidden and on processes whose outcomes were uncertain. The search for life around Alpha Centauri would require persistence, advanced technology, and a willingness to confront ambiguity. But the proximity of the system and the mounting evidence for planets ensured that the search would continue, driven by the tantalizing possibility that our nearest stellar neighbors might harbor worlds where life, like Earth's, had found a way to thrive. The observations from Webb did not merely add details to the picture of Alpha Centauri. They challenged fundamental assumptions embedded in models of stellar system evolution, planet formation, and debris disk dynamics. Each anomaly, when examined in isolation, could be accommodated through adjustments to parameters or invocation of special circumstances. But the combination of anomalies, a bright debris disk in a mature system, warm inner material, widespread ionized gas, connections to a distant companion star, suggested that the standard models were missing something systematic. Understanding what was missing required revisiting the theoretical frameworks that had guided interpretations for decades. Debris disk models assume that disks fade over time, as collisions grind material down and radiation pressure expels small grains. The timescale for disk dissipation depends on the initial mass of planetesimals, the collision rates, and the efficiency of removal processes. For a star, the age of Alpha Centauri A, models predict that debris disks should be faint, with infrared excess detectable but modest. The brightness of the observed disk exceeded these predictions by factors of several to 10, depending on assumptions. This could mean that the initial mass of planetesimals was higher than typical, that collision rates are being sustained by planetary perturbations, or that removal processes are less efficient than assumed. One possibility is that the models underestimate the longevity of debris disks around binary stars. The gravitational perturbations from a companion star can pump up eccentricities and inclinations of debris, increasing collision rates and sustaining dust production longer than in single-star systems. However, this effect has been studied in simulations, and while it extends disk lifetimes, it does not typically produce the level of brightness observed. The Alpha Centauri binary, with its moderately wide orbit, should not perturb debris as strongly as closer binaries, yet the disk is brighter than expected. Another issue involves the replenishment mechanisms. If comets are being continuously scattered into the inner system, where they sublimate and release dust, this could maintain the disk's brightness. But the source of these comets is unclear. The Oort cloud analogue around Alpha Centauri, if it exists, should have been depleted over billions of years by ejections and sublimation. Unless the system has an unusually massive comet reservoir, sustained replenishment is difficult to explain.